So we left off last time after introducing entropy, and we talked about entropy as being a driving force for spontaneity, essentially with the understanding that if the entropy of the universe, essentially if the dispersion of how the energy in the universe, if we spread out that energy and have more possible ways of spreading out that energy, we have more microstates, and that leads us to a spontaneous process. Okay, so we're going to look at entropy a little bit more today. So we talked about how entropy comes from, well, we started out with a really simple explanation where we had a number of conditions and a number of particles, and we kept it really simple, where right or left flask was our idea of position. But then we noted that, well, in reality, positions and energy come from a lot of different places. We have three-dimensional space, we have different types of kinetic energy, we also have bond energies associated with any type of substance. And so those things have to be taken into account also in terms of entropy. We talked about how the particles have separate states. The sum of all those particles together make up a microstate, and the number of microstates is related to that entropy of the system. We talked about it in a couple different ways, but it comes down to a fairly complex equation that we're not going to spend much time in, because the math involved in this is just beyond the scope of this class. It'd be more of a third year, fourth year, or graduate level, depending upon how in depth you go into the entropy. So the important part for us was really, and I'll get us to, so we talked about the simulation and how entropy increases just by being able to distribute energy in many, many more ways. So collisions between the particles that we did with our simulation allowed us to see, sort of visualize how entropy changed over the course of time. But in our simulation, remember, we had a curve, right? And that curve was just sort of a decay curve based on how that entropy was distributed amongst the 26 particles, which were, the collisions and the collisions between those particles. We had each particle started with one energy. After a certain number of collisions, the distribution of energy was, decreasing. For us, the understanding of how that translated into more possible microstates is sort of a key here. But that was only with one energy per particle. But as we saw last time also, the number of microstates is going to increase with more energy as well as with more particles. And so when we think about a given sample that has a certain amount of energy in it, and that energy is related to the kinetic energy of the particles, we can think about entropy being related to temperatures also. And so if we think about temperature and kinetic energy distribution, right? If you have a higher temperature, right? So if we have a high temperature, right? We have a lot of energy that's distributed throughout that system. You get this really broad range of kinetic energies of the particles. And so when you have more kinetic energy of the particles, you have more entropy of the system. There are more ways that you can distribute that energy amongst all of the particles of that sample, as opposed to when you have a sample that's at a lower energy, right, or a lower temperature, you have less energy to distribute. And so in either case, you get this type of a curve. And really, if we just threw more energy into our system and more particles into our system that we modeled last time, we would start to get a curve that looks more like this Boltzmann distribution. Hence, the entropy of a system is related to the Boltzmann constant, okay? But that's sort of an idea here. When you have more energy in a system, there's more entropy because you can spread that energy out in more different ways, okay? And so another thing to think about entropy-wise is entropy and phases. And so with water, we have solid, liquid, and gas as the three phases of water that we deal with. And one of the things we can start to think about is if we look at the entropy of a sample of water with respect to its temperature, which is what's in the graph at the right. And what you can see in this particular system is if you have a temperature at 0, there's going to be 0 entropy. There's no energy to distribute amongst that system, the particles that make up that system. As you increase the energy, right, as you add temperature, you're increasing the energy, so the kinetic energy of the particles goes up. And you get to a point where as you add more energy, right, going from 0 Kelvin all the way up to the melting point of water, as you add more energy, that entropy increases fairly linearly. But when you melt, right, something we know about melting, even with delta H's, right, the enthalpies, when we melt, okay, as the temperature, or as you add energy, the temperature doesn't increase, right? But what does increase is both the enthalpy, right, the heat of that solution, and then the entropy also. And so in the case of going a phase transition, right, something like melting, if you think about that, I'm adding a bunch of energy. Now these particles are going from really nice and compact, tightly spaced, and they're moving with respect to each other now. So in melting, the change in entropy, this delta S, you can call it delta S of fusion, right? That's going to be greater than 0 because the particles are moving more, there's more energy to distribute. And the same idea continues. If once it's all melted, as you add more energy, the entropy is going to increase until you go from the liquid to the gas phase. And when you go from the liquid to the gas phase, again, you're adding more entropy to that system because there's more energy to distribute. The particles are moving in more random directions, right? They're now spaced out with respect to each other, probably taking up a greater volume. And so if you think about boiling, the same idea holds, is that the entropy of vaporization, right, of boiling, is going to be greater than 0, which tells you that if I were to look at the entropy of a solid, that will be less than the entropy of the liquid, which will be less than the entropy of the gas. And that's something that we'll use going forward. But in particular, it's not just as simple as, hey, the entropy of the gas is a little bit larger than the entropy of the liquid. That distance, right, this here, right, that's a big change over here where we look at the entropy change associated with that phase change. So you can almost go over here and say, hey, that entropy of the gas is much greater, right, than the entropy of the liquid. And that's going to be something that's important for us as we start to do some examples where we predict entropy changes for some chemical reactions and processes. Okay. So we can now sort of look at entropy as it's related to phases as well. Okay. So the next thing here that we're going to look at is, so entropy in the second law of thermodynamics. The second law of thermodynamics states, in any spontaneous process, the entropy of the universe is increasing. Okay, so the entropy of the universe can never be less than 0. It can be either 0 or it can be greater than 0. Now, we can measure that for a process. Here's the thing. It's kind of a weird thing. Actually, this should be, well, we'll go through this. Saying the entropy of the change of the universe is less than 0, we actually write it down here, and it's not really the greatest thing to say because it doesn't really happen that way. So we're going to look at this in just a minute with a better understanding of things. But basically, if the entropy of the universe increases, we're going to have a process that is spontaneous, okay? And so the entropy change of the universe, all of the entropy out there, is going to equal the system's entropy change that we're looking at, that we're interested in, plus the system's, or the surroundings entropy change, the everything else besides the system. And so as we start to put this together, hopefully it'll make a bit of sense how this works. Remember, we're looking at the distribution of energy. And so if we think about a system in general and how that entropy change is related to, of the system is related to this entropy change of the surroundings, which is related to the entropy change of the universe, we can do that with the understanding that if we know that, so since delta S of the universe, right, is greater than or equal to 0, and we know that that's going to equal the entropy change, or greater than or equal, change this out here. We know that the entropy of the universe is greater than or equal to, actually that's not right either. What am I doing? Stop that. There we go. The entropy change of the universe is equal to the entropy change of the system plus the entropy change of the surroundings. You can sort of look at the entropy change of the system, right, as being opposite in sign to the entropy change of the surroundings, okay? And so that's going to be something that's important. So the idea here is if your system, for example, gives off energy to the surroundings, that energy is leaving the system, and so there's less energy to disperse, but it's going out into the surroundings. And generally, if you have energy going out into the surroundings, maybe as heat, it can be more dispersed by, say, if you're thinking about a chemical reaction that gives off energy in an aqueous solution, that energy is going to heating up the water, and that dispersal of energy to warm up the water is lost as heat, and that tends to be, so if you think about the chemical reaction as giving off that energy, the water is absorbing it, so the entropy of the water goes up as the entropy of the chemical reaction goes down. That's sort of a way of thinking about this. And if you consider a process, so process a little bit different than a reaction, in that we're not talking about a chemical reaction taking place, but something like water boiling where there's a physical change, right? If you have water that's boiling, okay, so that's a process that occurs spontaneously at 1 atmosphere and temperatures above 373 Kelvin, but it doesn't occur spontaneously at temperatures below that. So the sign of the universe and the magnitudes of the system and the surroundings are going to be important for the spontaneity of a process like boiling. And the magnitudes of the entropy of the system and the entropy of the surroundings are going to have an impact on the overall entropy change of the universe. And so we can start to see this in a little bit more of a derived way that will get us to a point where we can start to see whether a process is going to be spontaneous or not. And so one way we can think about entropy changes of the system and surroundings is really through heat flow, okay? And so what we can look at here is if you think about the change in entropy of the surroundings, okay? So you have a system that you're working with and you want to think about, okay, so the system could be a reaction, could be a process, but when you think about the entropy change of the surroundings, it's usually determined by the flow of heat in one direction or another, because energy, based on heat flow, can flow into or out of a system, which means that it's flowing out of or into the surroundings. So if you have an exothermic process, the heat goes from the system into the surroundings, sort of like we were talking, something that we can consider for that would be a chemical reaction, that chemical reaction that we talked about in water, right? So if that heat goes from the system, that chemical reaction into the surroundings, how does it affect the particles in the surroundings? Well, if it's heat, we're looking at kinetic energy, right? The heat is related to the kinetic energy of the particles. And so what you're doing is you're increasing the random motions of the molecules in the surroundings, right? So if you have an exothermic process, the surroundings, the entropy of the surroundings are going to increase. And not only that, if you think about something like heat and the entropy of surroundings, when you're talking about an example like a chemical reaction that takes place in water, right? That chemical reaction, if it's exothermic, now that energy goes out into the water. As soon as the bonds break and new bonds form, that chemical reaction occurs, as that energy goes into the water particles move faster, and the water particles, as they move faster, they collide with other water particles, and essentially as they collide, it transfers energy out away from the chemical reaction that has occurred as heat. And so that energy becomes more dispersed, and it's harder to bring it back in. And so you have more ways of distributing it as that energy sort of goes out away from the particles that are reacting, those reactant particles that react. And so generally, when you think about a chemical reaction occurring, you're looking at how the surroundings are really affected by that process or chemical reaction. And so when we look at the magnitude of the entropy change of the surroundings, it turns out that's going to be dependent upon the temperature at which the heat is transferred. So you can think about it in this way, right? We're looking at an entropy change within the surroundings. If I have a chemical reaction that gives off energy to the surroundings, if those surroundings are at a very low temperature, any amount of energy that the surroundings absorbs gets dispersed and causes a somewhat large change in the entropy of those surroundings, right? If you add a little bit of heat to some cold water, those particles start moving around, and you can think about the original entropy as being very low, but even a little bit of heat is going to cause a pretty good amount of extra entropy, right, in the surroundings. But if that chemical reaction or process occurs in an exothermic way at a higher temperature, right? Well, those particles at a higher temperature in the surrounding already have a lot of energy to them. So adding a little bit more is going to have less of an impact overall than if you add that energy at a lower temperature, right? It might have a ton of energy already because it's at a higher temperature. So adding a tiny bit more really isn't going to make that big of a difference, right? And so when we think about the magnitude of the entropy change in the surroundings, it's going to depend on the temperature at which that heat is transferred to the surroundings, right? If the heat is transferred at a high temperature, it's going to be a small impact on the entropy of the surroundings. A lot more energy already in the surroundings to deal with. But if it's transferred at a low temperature, the impact will be much larger, right, on those surroundings. So that's something to think about also, right? The entropy change of the surroundings and how much it absorbs the energy, that entropy change is going to be temperature dependent. Okay, so when we think now about a driving force for a reaction being provided by heat flow, and that driving force is temperature dependent, then we can start to think about the magnitude of the entropy, right? If it's based on something like heat flow, you're interested in the quantity of heat flow, okay? So the more heat flow, the higher the entropy change, but it's also dependent upon the temperature because there's already heat out in the environment. And so you can look at the entropy change of the surroundings as being dependent upon the heat in the surroundings divided by the temperature at which that heat is transferred. Okay. Now, just for an exothermic process, something to think about, since the heat associated with the surroundings is a positive value, right? In an exothermic process, remember exothermic, this is exothermic for the system that we're interested in. Okay, so for that system, yeah, the heat is going out of the system into the surroundings. So the heat of the surroundings is increasing, and temperature is always a positive value. So you're going to have a Q over delta T that's greater than 0. Okay, if you think about an endothermic process, right, the Q, right, if it's an endothermic process, the Q will be negative, and so the entropy change of the surroundings will be less than 0. Okay. Now, remember we have a couple of things that are governing the spontaneity. It's not just entropy of the system and surroundings, it's the entropy of the universe. And so the magnitude of that entropy change of the surroundings is going to have a great influence on the process being spontaneous or not. So, and keep this in mind, right? When we talk about Q of the surroundings, that's the heat transferred to the surroundings, right? So if it's exothermic, the heat is coming from the system to the surroundings, and if it's endothermic, it's going from the surroundings to the system. So we've now kind of defined, if you will, the entropy of the change of the surroundings as being equal to the heat transferred to the surroundings at a given temperature. Okay. So, how is this related now to the entropy and the heat associated with the system? Well, if we go back all the way to chapter 6 stuff, when we talked about heat, right, we also said, hey, the heat of the system, right, is equal to the enthalpy change of the system at a constant pressure. And we were a little hand wavy with this at the time, but the whole idea is when we talked about enthalpy back in chapter 6, right, we said the enthalpy, so the enthalpy H is equal to E, the energy minus the work, right? And so we said, okay, well, when we think about the energy transferred into the system, this work piece kind of goes away because we're talking about pressure volume work. And so we said, oh, the energy change of a system is equal to the energy that goes into the system, and that's related to heat. And so that was something we did back in chapter 6. I'm not going to rehash that much right now. Suffice to say, we equated the heat associated with the system to the enthalpy change of that system, okay? And so when you think about the heat associated with the system, we're talking about, remember those bond enthalpies? We used average bond enthalpies, we used enthalpies of formation, we used Hess's law, all to do some calculations of the enthalpy change of reactions. So that was related to the heat of the system, okay? Now, the heat going into a system, Q, right, or the energy going to the system is related to that heat. So Q is equal in magnitude, right, but opposite in sign to the heat that's coming out of the surroundings, okay? So what we can think of there is Q of the system is equal to negative Q of the surroundings. We did that when we looked at our calorimetry, right? Assuming all things are equal when we do this, we say, okay, well, in general, the system is just going to give off its energy to the surroundings, and we can say that it's equal in magnitude, opposite in sign, which means that the heat change of the surroundings is going to be related to the enthalpy change of the system. And we want to put this together because the enthalpy change of the system, if it's a chemical reaction, we're talking about bonds being broken and bonds being formed. But that gives us a slightly different definition for the entropy change of the surroundings. So the entropy change of the surroundings will be related to the enthalpy change of the system over the temperature at which the process is occurring, okay? Now, when we think about the entropy for a system, okay, just briefly, we'll talk about this, but we'll just want us to think about it. When we think about the entropy for a system, okay, in a chemical reaction, right, we're talking about chemical reactions, so bonds broken, right? Excuse me. Bonds broken and bonds formed, right? So when we have bonds broken and bonds formed, that's structural relationship. That has a structural relationship to the entropy. More complex molecules have more entropy to them because of different ways that those the bonds can stretch and bend, and the different ways the molecule can tumble. So when we think about the entropy of a system, the entropy of a system is structurally dependent, okay? So when we think about the surroundings, the entropy change of the surroundings is based on heat being absorbed by the surroundings. When we look at the entropy change of a system, we're looking at the entropy change of the substances, right? The reactants entropy versus the products entropy. And so those are going to be sort of the different ways to look at the entropy of the system versus the surroundings. Okay, so we can kind of put this together, but we're going to put it together in a little bit of a different way. We kind of approach it from a different position. And that's by introducing this new thing called free energy, or Gibbs free energy. Okay, it's also the Gibbs free energy of what we're looking at. So the entropy of the universe, that predicts spontaneity. But there's another function that does that, that's called the Gibbs free energy. And that also predicts spontaneity. And the Gibbs free energy, G, is equal to H minus TS. Now, similar to how we deal with enthalpy, we often don't look at just the overall free energy of a system. We look at it more from a standpoint of a change, because we're interested in processes that are chemical reactions or processes that occur at a constant temperature. So what we will tend to do is look at the change in free entropy of a system for something like a chemical reaction or a process. And that would then be equal to the change in the enthalpy of that system. If this is done at a constant temperature, it's going to be equal to, or the enthalpy minus T times delta S of the system. Now, if we know, or if we go in and we were to divide each side by the temperature, we would find that, okay, so you divide each side by the temperature, right? Those go away, right? You wind up with, actually I should say by negative T, that goes away. Divide by negative T, that goes away. And so what you wind up with here is an equation that looks like this, where you have negative delta G of the system is equal to negative delta H of the system over T plus delta S of the system. Now, something we noted from the last bit that we've been talking about is that the delta S of the surroundings is equal to the negative of the enthalpy change of the system over the temperature. And so we can plug that in over here, changes our system around. And you'll notice that over on this side of the equation now, we have an equation that looks like something we had before, where we saw that the enthalpy change, or excuse me, the entropy change of the surroundings plus the entropy change of the system is equal to the entropy change of the universe, okay? And so what you can essentially do from this top equation here and this equation here, you can see that the entropy change of the universe is going to equal the negative of the free energy change of a system divided by the temperature at which that process or reaction occurs. And so when you look at this, and you know that if you have a delta S of the universe, actually I guess I have this on the next page. You know that the delta S of the universe is, if it's greater than 0, that leads to a spontaneous process. Because there's a negative sign in front of the delta G, then this free energy of the system divided by the temperature, if that is less than 0, that will also lead to a spontaneous process. And so what that kind of allows us to do here is it allows us to predict, essentially, under what temperature conditions a reaction will be spontaneous, because not all reactions are going to be spontaneous at all temperatures. And so keeping in mind, thinking about something like melting, right? Melting would be spontaneous at temperatures, right, above 273 Kelvin, right? And freezing, right, at temperatures below 273 Kelvin. And so you can use this other function, this delta G function, okay, to predict spontaneity. And so what we're going to use a lot of time to predict spontaneity is that the delta G of the system, okay, so that's equal to what we got from the last slide, this delta H minus T, that should be of the system, minus T delta S of the system. And we can use this equation to help us predict whether a reaction is going to be spontaneous or not. If you have the enthalpy change of the system minus the temperature times the change in entropy of the system, if that value is less than 0, then you're going to have a spontaneous process. So what this means sign-wise, because we're going to do some examples where we do some calculations of this. But if you look at the enthalpy change of a system, that's an enthalpy change that we can calculate in a few different ways. You can do that using Hess's law. You can do that with the enthalpies of formation like we did in chapter 6. Okay, so you can calculate that value. If it's, remember, if it's greater than 0, then it's endothermic. If it's less than 0, it's exothermic, right? So that's stuff that we had some experience in the past. And that's going to have the sign of the delta H will have an effect on spontaneity, but also the sign of delta S will have an effect on spontaneity. So you can think about something like, melting, where the where the entropy increases, or freezing, where the entropy decreases. And so the sign is going to depend upon the process, right? For the entropy. So we can look at it where under certain conditions of enthalpy and entropy for a process, those entropy changes and enthalpy changes can lead to a process that's spontaneous at all temperatures, or it could be spontaneous at no temperatures, or it can be spontaneous at certain above a certain temperature, or spontaneous below a certain temperature, depending upon the signs of delta H and delta S. So if you have a delta S that is, delta H that is negative, okay, if we think about for enthalpy changes, right, negative is good, right? Enthalpy change that is negative means you're going to an overall free energy that is lower, right? And so the enthalpy change being negative, well, if I think about this in the context of the equation, right, I want, in order for a process to be spontaneous, right, that delta G has to be less than 0. So if the delta H is already less than 0, we're on track for good things. So if the delta H is less than 0 and the delta S is less than 0, because we're subtracting off T times delta S, where T is positive, and if delta S is positive, then that's going to always lead you to a delta G that is negative, right? And so if the enthalpy change is negative and the entropy change is positive, at every temperature, okay, you're going to have a value of delta G that's negative. And so a process will always be spontaneous if the delta H, right, is negative and the delta S is positive. The opposite of that, right, where delta H is positive and delta S is negative, well, that's going to lead to a positive delta H and the term negative T delta S. If delta S is negative, that's going to lead to a positive negative T delta S. And so when you put those together, you're always going to have a process that is not spontaneous, or is spontaneous in the reverse direction, because the delta G of that system is going to be positive at all temperatures. It's when you start to get into the enthalpy and entropy changes that are the same sign. So if they're both positive, right? If these are both positive values, the enthalpy change is positive and the entropy change is positive, then what you really have to look at now is say, okay, if enthalpy change is positive, right? Positive, right, is sort of not good for spontaneity for the enthalpy change. Okay, negative is good for spontaneity. Okay, for S, the S, if you have an S that's positive, that's good for spontaneity. And if S is negative, right, the delta S is negative, that's not good for spontaneity. So you're really looking at the two figures, this delta H, this enthalpy change of the system, and really it's the negative T delta S of the system that becomes important. And if they're both the same sign, then the temperature becomes a really, really important factor here. In fact, if they're both positive, then in order for the negative T delta S to overcome the magnitude of the positive value of the delta H, right? Because if delta S is positive, then the term negative T delta S is negative. In order for that term to overcome a positive delta H, that T has to be relatively large, right? Large enough to turn that this piece, right, this negative T delta S is bigger than the delta H of the system. And so at high temperatures, right, at high temperatures, this whole term starts to take over this equation, okay? So at high temperatures, for a process that is endothermic, but has an increase in entropy, at high temperatures, that increase in entropy is more important and it takes over and you get a spontaneous process. At temperatures below a certain temperature, and we'll look at how to calculate that temperature in a minute, at temperatures below that specific temperature for the process, it's not going to be spontaneous. And then the reverse is true, right? So if you're looking at a process that has a negative enthalpy and a positive or a negative entropy also, right? So you're losing the entropy for that system, which means that energy is coming, or in some way is coming from the surroundings into, from the system out into the surroundings. You're giving off entropy. It's getting out there into the surroundings somehow. Then you're worried about, well, how much of that entropy is important. And so under those circumstances, at lower temperatures is when that negative T delta S, right? At lower temperatures, if they're both the delta H and the delta S are negative, at lower temperatures, the negative T delta S is small compared to the magnitude of the delta H. And so at lower temperatures, the delta H, right, is going to be the important term there. And if it's a negative value at lower temperatures, you're going to have a process that's spontaneous. And at higher temperatures, the negative T delta S term will become positive and much larger in magnitude above a certain temperature that it'll overtake the enthalpy change of the system. Okay. So how do we determine that? Well, in order to determine the temperature at which a process goes from spontaneous to non-spontaneous or vice versa, right? And this is a key. When it goes from non-spontaneous to spontaneous, it's going to be for a process that has both the delta H and delta S are the same, okay? This is going to be kind of a good little roadmap. If delta H and delta S have the same sign, that's when this process becomes important. Because under the first two circumstances, where delta H and delta S have opposite signs, it will be always spontaneous or never spontaneous, or spontaneous at all temperatures, or never spontaneous, or spontaneous at no temperatures. But if they're the same sign, well, and they're both positive, okay? If they're both positive and they're the same sign, then you're going to have a delta G at high temperatures that will be negative. Okay, that's an important one here. If they're the same sign and they're both negative, then the delta G at low temperatures will be spontaneous. And so understanding that the signs of the delta H and the delta S are going to relate are going to relate to us the spontaneity of the reaction, we can now go and say, okay, we can determine a temperature, or the temperature at which it goes from spontaneous to non-spontaneous, because the idea, or non-spontaneous to spontaneous, if we have a delta G that's positive, right? Positive delta G means it's not spontaneous, right? To negative, the negative delta G says it's spontaneous. So when does delta G switch from positive to negative? Well, it switches at 0. And so what we can say is that we can figure out that temperature at which it goes from negative to positive or positive to negative by determining at what point, at what temperature is the delta G 0. So if we look at boiling, right, the process of boiling, so we're taking, remember this is just a process where water as a liquid goes from water as a liquid to water as a vapor. And we're interested now in the enthalpy of vaporization and the entropy change of vaporization, and what temperature that process would be spontaneous. So what we can do is really just set the delta G equal to 0. Okay, so you can say delta G of vapor, so delta G equals 0 at the point where the enthalpy change, so the enthalpy change, we're just going to take this from up here, 40.68 kilojoules per mole. Minus T times delta S, which is 108.8 joules per mole Kelvin. Okay, and you basically just solve for T. But something to keep in mind here, I'm going to rewrite this and I'm going to change my units. You can do it either way. You can either do it from, you lose the kilojoules by putting in the scientific notation, or you can lose the joules, or you can change your joules to kilojoules. Depends upon how you want to do it, what makes you more comfortable. Basically, you say that would be equal to 40.68 times 10 to the third joules per mole minus T times 108.8 joules per mole Kelvin. So that's something to keep in mind, is the values for entropy tend to be in joules per mole Kelvin, where the values in enthalpy tend to be in kilojoules. Okay, so keep that sort of at the back of your mind when you're doing some of these questions. And so all you have to do is say, okay, so 40.68 times 10 to the third joules per mole Kelvin, excuse me, per mole, or be careful with those units, right, is equal to T times 108.8 joules per mole Kelvin, and you can divide each side by that entropy change. Okay, and so what winds up happening, the joules per mole cancel out there and there, whole terms cancel out there. So you wind up with the temperature, right? The K here flips up into the numerator, and your temperature should wind up being 3, if you just do that calculation, 73 point, if you do this one, like 89. So you're in the ballpark of what you would expect for the boiling temperature of water, okay? So 373.89 Kelvin, or you're right, 3, right, 73, 3, come on, 373 0.9 Kelvin. And this may differ, right, from our basic value of 373.15 that we've had in the past, because we're also making an assumption when we do these particular calculations. Okay, we're making this assumption. And this isn't one of those assumptions like back in equilibria that you have to check. The assumption that we're making here, and it's a relatively okay assumption. We'll write it down and we'll talk about it. The assumption is that the delta H for the process, so in this case, of vaporization, and the delta S of vaporization are constant for all temperatures. And it's a pretty good assumption. We're saying essentially the enthalpy and the entropy of vaporization, no matter what temperature you're doing that, or for any process, not just vaporization, could be freezing, could be a reaction. For any process, we're assuming that those values are relatively constant for all temperatures. And in most cases, that's a pretty good assumption. That's a pretty good model for what we're doing. Now, it's not perfect. Turns out the enthalpy of vaporization does change depending upon the temperature, but it changes by a small enough amount to be unimportant for most of these predictions. Remember, we're predicting whether a reaction will be spontaneous or not. So that's one of the keys here. We're doing this assumption that the enthalpy of vaporization, or the enthalpy of the process or reaction, and the entropy of the process of change of the process or reaction are going to be constant at all temperatures. And that's an assumption we're going to make through a lot of these types of calculations, okay? So now we know, so getting back to our problem, we know a couple things, right? We now know the temperature at which this reaction goes from non-spontaneous to spontaneous. Okay, we also know delta H, right, is greater than 0, and delta S is greater than 0. And so what that means, if we think about the delta G is equal to delta H minus T delta S, we want the minus T delta S term to be the important term, right? So we want this to be large, okay? If we want that to be large, and we know that our temperature, this 373.9 Kelvin, right, is our cutoff, then that means that temperatures above, right, 373.9 Kelvin, this vaporization will be spontaneous. Okay, so that's sort of what we're getting there. We can solve for the temperature, and when you solve for the temperature and you also know these things here, that leads us to the conclusion that temperatures above that temperature are going to be spontaneous, okay? And that's how you'd predict the spontaneity of a reaction given some thermodynamic data. Something we're going to do a little bit in a little bit is actually looking at predictions where we actually have to determine the enthalpy change of a reaction or process and the entropy change of a reaction or process as well, okay? And so that's kind of the next step here. Predicting entropy changes. Now, there are a couple ways of doing this. Now, if you want a specific entropy change, you have to do a calculation of some sort, and we'll look at those calculations, okay? But in general, we can make predictions based on certain things. And those certain things are sort of what we started out today, which is the entropy changes of the processes or reactions in which we're dealing with certain phases, okay? Since we know that the entropy of the gas phase, there we go. So since we know the entropy of a gas is much larger than the entropy of liquid or solid, okay, since we know the entropy of a gas is much larger than the entropy of a liquid or the entropy of a solid, for any specific system or reaction, we can predict the entropy, the sign of the entropy change, by looking at the moles of gas, or the delta in gas, the change in moles of gas, right? So this is the one that we looked at way back when we were looking at equilibria, okay? And so in this case, if you have a delta in gas, remember delta in gas is going to equal the moles of gas on the product side minus the moles of gas on the reactant side. And that's just based on the stoichiometric coefficients ahead of any of those gas substances in the chemical reaction as written. So if you have a delta in gas that's positive, right? A positive value for delta in gas means that your change in entropy of the system or of that reaction is going to be positive. If you have a negative delta in gas, well, then you're making fewer moles of gas in the reaction. So if you have fewer moles of gas on the product side than you did on the reactant side, and so you're going to have less entropy after the reaction occurs because you've made less gas. And so you're going to have an entropy of the reaction that's negative. If, however, the moles of gas are the same on either side, then you have to do a little bit more because you can't really predict the sign of the delta S for that reaction. And so if you have the entropy change of the reaction is something that you have to calculate, you can use this equation, which is similar to the equation that you use to calculate the enthalpy of a reaction using the enthalpies, the standard enthalpies of formation. And so that's kind of where we're going to go a little bit next in some of these examples. So the first thing is, where would you find useful data for doing some of these things? Okay, and you'll find that in a table of standard entropies or standard enthalpies, basically a table of thermodynamic data. Okay, and so what you have in one of these tables is a substance. So this is whatever chemical compound is there. You'll find a column for the entropy or the standard molar entropy of that substance. Remember, since entropy has a 0 point, we don't need to use it as a relative value, right? Like the enthalpies of formation are relative to the elements in their standard state. Here, we're looking at the standard molar entropies. And another column is the standard enthalpies of formation that we did back in chapter 6. And here we've got another column that is the standard free energy or the standard Gibbs energy of the formation for that same compound. Now you'll notice that anytime we have an element, silver solid, right, there still has entropy, even though it doesn't have enthalpy change or delta H of formation or a delta G of formation. You'll notice if you have the element, the enthalpy and the free energy of formation are both 0, right? Because of our definitions of what those meant back in, or what the delta H of formation meant that we looked at back in chapter 6, you get the same thing from the free energy, right? You're basically taking that substance and making it from its elements. The entropy, though, remember the entropy is a standard entropy. And at 0 degrees, or excuse me, at 0 Kelvin, right? At 0 Kelvin, the entropy would be 0. But at 25 degrees Celsius or 298 Kelvin, each of these substances will have some measure of entropy associated with the energy that's dispersed throughout that substance. And this is an entropy per mole of that substance. So those will only have 0 values at 0 Kelvin. Okay. So this table is one that we're going to go look at when we start to do some of these processes. And we're going to use this table in the upcoming examples. But basically, you could look these values up and do the calculations as you've done in the past with enthalpies of formation. So when it comes to something like diamond and graphite, right? Graphite has 0 enthalpy of formation, 0 free energy of formation. Whereas carbon, as diamond, has a slightly higher enthalpy of formation and a slightly higher free energy of formation. And so that's something to keep in mind as we go through this. But we can just look these up as we need to. And so that's what we'll come back to. And so you'll have the substance, the standard molar entropy, the enthalpy of formation, standard enthalpy of formation, and the standard free energy of formation. So our example we're going to look at here is the following. Predict the entropy change of the reaction, the standard entropy change of the reaction, for H2 plus O2 goes to form 2H2O. So the first thing we should always do when we have a question like this, so we can predict the sign of it very easily, right? We can predict the sign and say, well, this is 2 moles of gas. Here's 1 mole of gas. All right, so we have a total of 3 moles of gas there on the reactant side. We've got 2 moles of gas on the product side. And so you could say your delta in gas is equal to 2 minus 3, which is equal to -1. And since -1 is less than 0, you would expect your delta S of the reaction to be less than 0 as well. Okay, so that's our prediction. Okay, but since we have the values here, we can do the calculation relatively simply. We'll do this, should have room on this page. So what we can do here is knowing we have 3 things, right? We've got the H2, so we can go and look at our standard entropy of H2. And so we can just go back up to our table and right down here, there's H2. So 130.7 joules per mole Kelvin. We can find our entropy of O2. Go back up to our table, and that's going to be over here. All right, so 205.2 joules per mole Kelvin. Okay, and then we can have our standard entropy of water. And we go back up here, we find water is down here, and we're in the gas phase. We're going to take this one, and we've got a value of 188.8 joules per mole Kelvin. Okay. And so now all we have to do is use that equation. So this equation here, right? So this is the equation we want to use, the sum of the stoichiometric coefficient of the products times their standard molar entropies minus the sum of the standard or the stoichiometric coefficient of the reactants times their standard entropies, and we can do that here. So if we start with our products, we have 2 moles of H2O. Right, that's just coming from our stoichiometric coefficient, times the standard molar entropy, so 188.8 joules per mole Kelvin, minus 2 moles of H2 times 130.7 joules per mole Kelvin, plus 1 mole of O2 times 205.2 joules per mole Kelvin. Okay. And so our unit-wise, these will cancel out, right? Moles and moles, moles and moles, and then here, moles and moles. And so we would get values of 377.6 joules per Kelvin minus 261.4 joules per Kelvin plus 205.2 joules per Kelvin. Okay. And you do that math, you wind up with negative 89 joules. Where did I lose you? Anybody? All right, guys. Where do we need to go back to? Am I here? You guys there? Is anybody here? Anybody there?
Yes.
Okay, how long ago did I lose you?
We got through doing all of the equation and canceling the moles out.
Okay.
And then, yeah.
Okay, so let me go back to this. Okay, so we're right about there then. So it died quickly then. Okay, thanks guys. So basically, if you take and just run the math through the math, you wind up with a value of negative 89 joules per Kelvin, which you get here. And that does turn out to agree with our prediction, right? That we would have a delta S of the reaction less than 0. Okay. So that's just a quick prediction of the entropy of the reaction initially. And then we confirmed that what we expected, right? An entropy of reaction less than 0 because the delta in gas is less than 0. If, however, you have a situation, and I put in the values for the entropies of the different reactants and products here, so we wouldn't have to go back to the table. But if you have a situation where you have, say, the same number of moles of gas on either side, right, then you know, so if delta in gas, right, is equal to 0, what happened? If delta in gas is equal to 0, right, now you have to do that same calculation in order to find the standard entropy of the reaction. And so your standard entropy of the reaction, for this one, again, products minus reactants. So you've got 2 moles of aluminum solid, and your standard entropy of standard molar entropy of aluminum, so 28 joules per mole Kelvin, plus 3 moles of water times 188.8 joule per mole Kelvin minus the entropy of the reactants. So 1 mole of aluminum oxide times 51 joules per mole Kelvin plus 3 moles of H2 times 130.7 joules per mole Kelvin. And so we can just go through the calculation. You'd have 56 joules per Kelvin, right? Moles cancel, moles cancel. So you'd have 56 joules per Kelvin plus moles cancel, 566.4 joules per Kelvin minus moles again cancel, you're left with 51 joules per Kelvin plus 391.8 joules per Kelvin. Right. And you just add those up. 622.4 joules per Kelvin minus 442.8 joules per Kelvin, and that would give you a value of 179.6 joules per Kelvin for the entropy change of this reaction. Okay. And so what we'll do is, I think, yeah. So we'll end this one here. So where we've now dealt with entropy changes pretty significantly and calculations of entropy changes. And we've looked at a little bit of free energy changes for chemical reactions. And so we'll end that here because there's quite a lot to chew on, I know, from this particular lecture. We'll spend a bit of a short lecture tomorrow and sort of finish up chapter 17 on Thursday. And so we'll stop recording.